Hi everyone, yeah, so thanks very much for coming to my talk. My name's Levie, and I'm going to be presenting on accelerated, segregated, finite volume, linear elastic solid mechanics solvers using machine learning, a title that really rolls off the tongue. So yeah, thanks. So the overall aim of my PhD is to try and speed up OpenFOAM solvers using machine learning. So a good place to start, I decided, was a segregated linear elastic solid mechanics solver and solves for foam because it's relatively simple. So yeah, what do I mean by speed up? By speed up, I mean a method that produces the same result as conventional methods, but in a shorter total time. Pretty simple. And also a method that's useful. So a method that people can actually replicate and use with ease. So just to run through quickly of my approach, the approach is for a specific test case is to run that test case on a coarse mesh, then train a machine learning model to predict the converged solution of this coarse mesh, and then rerun the case on a fine mesh by using the machine learning model to predict the solution. So the hypothesis is that the total time taken to run these steps is less than the total time taken to run the fine mesh case conventionally in OpenFOAM. So a solid mechanics solver, what does it solve? It has one governing equation, which is conservation of linear momentum, which you can see here, where U represents displacement, not velocity. And so for linear elasticity, we have this constitutive law, which assumes small strains and rotations, which basically means that the strains and rotations are negligible with regard to the mesh, so the mesh actually doesn't move from time step to time step. So this is solved like so in solids for foam by inserting that constitutive law into where the stress is. And yeah, so solids for foam, how it solves this in a segregated manner is it uses this correction term here. So these two terms are actually identical. And one is treated implicitly, one is treated explicitly, and then the rest of the equation is as so. So how are these solvers solved? I'm sure you've all seen this before. The linear system, we have a matrix an A matrix with implicit coefficients, our U and our B full of explicit coefficients. So segregated solvers, they solve three of these systems separately. So one in each dimensional direction. So one in X, one in Y, one in Z. And the B vectors then, they're a function of the displacement solutions from the previous iteration, as you can see here. So, as I said, once the solution is found in one system, this is inputted into the B vector or used to get the B vector for the next iteration for each direction. And this happens multiple times until we get a converged solution. So how do we get it? What's the converged solution? Converged solution in segregated approach, we use a relative residual. So we basically find a solution where it's close enough to the previous iteration solution, which is what capital U is here. That just means U field in all directions. So why am I telling you this? Well, this method creates a pattern. So a pattern of U fields that all differ from iteration to iteration. And what does machine learning do? It can predict patterns. So what does this pattern look like then? Just for a simple plate hole test case, it's pretty basic test case in solid mechanics. As you can see here, traction on the right, the set above it isn't too important. So if we just look at the displacement for one highlighted cell here, you can see here on the left that starts at one value at the first iteration, and then all the way to convergence, it converges to some value, and the same for the Y direction. So pretty standard. So let's compare the converged solution in a coarse mesh and a fine mesh. So the coarse mesh has 1,000 cells, and the fine mesh is 100,000 cells, so 100 times finer. So you can see here that I've highlighted the pink dot here. So they're similar locations compared to the fine mesh. So yeah, the fine is in orange here. So you can see the convergence pattern for this one cell. It's pretty similar to the coarse mesh, as you all would probably expect. and it's the same in the y direction. So I guess you would think that a machine learning model would be able to predict the fine mesh based on the coarse mesh. But you might say, sorry, as I said here. So you might say, well, that's just one point. So I can't show you all the points because it would be a mess. So I'll show you a subset of the points. So all in the same area. And this area is the highest displacement in the x direction. So theoretically, the fine mesh should be greater than the coarse mesh because you're going to get a more accurate result, which is shown here. So these orange plots, they're loads of plots because there's loads of points. So these are the fine mesh plots, and then the blue plots are the coarse mesh. Oops, sorry. So yeah, so what we can take from this is that if we were to make a machine learning model with this, using the coarse mesh as our training data, and then trying to predict on a fine mesh, that the majority of the points would be interpolating. So machine learning models like to interpolate. Normally, they don't like to extrapolate. So the extrapolation would only occur for a small proportion of the fine mesh case. And I guess the hope is that the small extrapolations machine learning model has to make doesn't affect the overall convergence. So yeah, so how will this machine learning model look? So as I've shown you, this pattern here, we've D's, sorry, I've changed from U to D's, but in solids for foam, we use D's for displacement. So it'll be D's from now on. So yeah, so we have a set of iterations and a final solution. So the input data will be the displacement fields up to a certain iteration, and the output data will be the converged solution. So how does this look more closely? We'll have, 3 by n will be the size of our input features. So we'll have 3 by n input features. So we'll select the training iteration n, and then we'll have a final iteration as the output. And each data point in the model will be represented by a cell. So yeah, as you can see here. So then when we try to implement this, what will the solution procedure look like? You'll run the coarse mesh. So in this case, I think it takes 2 seconds to run. So this is on a basic case, so bear with me. Then train the machine learning model on the coarse data, which I think takes about 20 more seconds. And then we'll run the fine mesh case as normal. And then at 20, we'll make a prediction. And then we perform a traction loop, but I'll explain in one moment. So yeah, so the first is to run a coarse mesh. Why have I picked 20? I kind of played around with this. I thought 20 was a good enough number. If the final iteration, sorry, I didn't mention here, is 229, I thought it was a big enough number that it would have enough information, but not too big that it would prevent speed up. So yeah, so these are stored. This is what it looks like, sorry, in our one directory. So all the fields stored there. So yeah, just again, the inputs and outputs, but instead I've actually put exact numbers on it this time. So the model I'm using is just a simple feed-forward neural network in Keras TensorFlow. And the actual architecture is pretty arbitrary, I guess. So I kind of changed the architecture a few times, but what I noticed is that it doesn't really matter too much, the architecture. You can change it and you get similar results, but the most important part is to have a low training time, so about 500 epochs to train. So yeah, so I'll walk you through what this looks like. So we run a fine mesh case till 20, make a prediction, and then we have to perform a boundary traction loop. So what this means is because solids for foam sets up this implicit-explicit correction, it means that sigma is dealt with explicitly. So we have to, and we're only predicting for the internal cells, not for the boundaries. So we need to find basically a stress field, a D-boundary field, and a grad D field that all makes sense, for lack of a better word. So it loops through this code, which I won't go through in detail. And yeah, after the prediction, this basically sets up the boundary. So does this work? Yes, it works. So when I do this for the exact solution, it converges straight away. So I've inputted the fine mesh solution here and it converges straight away. So yeah, that's just a bit of a side note. So yeah, then after the prediction, I allow this to converge. And this is the first set of useful results. So as you can see here, the iterations are lower, so a lower total amount of iterations, which is good. But how much time does an iteration take? I guess no iteration is made equal. So if I change make that bigger, change the y-axis to time, and you can see straight away that these iterations actually iterate faster than the usual ones. So this gap up here is the time taken to run the coarse mesh and train the machine learning model. And then this little gap or spike here is the time taken for the traction boundary loop. And for a residual of 10 to the power -5, which is what it recommends in the literature for this case, produced a speed up of 54.4%, which is pretty good. So you might say, well, Scott, we already have the coarse mesh solution. Why don't we just interpolate this to the fine mesh and let it converge normally? So it's a good idea. So I've compared it to this, which the green slope is. So this is kind of, I think, what multigrid is based on, but I haven't delved into the world of multigrid too much yet. But this is just a simple comparison. So even with this, it's still at around a 34% speed up. So I tried those on other test cases with the exact same parameters, and yeah, it works. Maybe not as well. So 27% speed up, which is pretty good. Then with the narrow T member case, similar refinement ratio, not as good when compared to the mapped fields case, but pretty good compared to conventional methods with about 13% speed up. And you can see also here, sorry, I didn't mention, these are also 3D cases. So the time is a lot longer. So these take about an hour to run. So yeah, then I'll just brush over some other methods I kind of played around with. One was to offset the first two iterations, so not use the first two iterations. This showed better speed up, so 50% to 27% for just the elliptical plate. And then I also made multiple predictions. So I used two separate machine learning models, one to, this is easier, one to make a prediction here and one here. And it increase the speed up by about 10%-ish. So yeah, so to conclude anyway, what have I shown? I guess I've shown that this method can be used to speed up specific test cases when you set a specific set of parameters. So the parameters being the refinement ratio of the test cases, the number of training iterations, the machine learning architecture training time, and these different methods, how these parameters can be tuned or so, I'm not too sure of. That's one of my next steps. So to come up with some rule of thumbs for how to make this better. But yeah, so next steps would be to learn how these parameters change from case to case, maybe try it on different solid models and different physics like fluids or FSI. So yeah, thanks very much for listening to my talk. Yeah. That's a good question. I don't have to hand. I trained it off. I think I used MSE, but I guess I'm not doing the conventional training test split, and I'm kind of just using the time period. So I'm getting a rough time amount and saying that's how much I'm going to train for. If that makes sense, as opposed to using a loss function. Sorry? Yeah. So yeah. But the output is the coarse mesh solution. Yeah. So, no, just on a computer. So this is still kind of high level stuff. So it's only on a Faster, yeah, okay, yeah. So that's another thing I can add to the future work, but I mean, I guess this is just proof of concept per se. Yeah. Yeah. Yeah, I don't have it. I didn't include it, but it's say for this one here. I think to run the course mesh was about 2 seconds, and then the rest is the machine learning training. So it's about, I think it's about 20 to 30 seconds. So it's not a big data set. It's 1,000 points, so it's not gonna take too long, I guess. Yeah. 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 Exactly. Yeah. I haven't. That's one thought I had. Yes, whether to. I think maybe to use the map fields on the boundaries, but no, I haven't combined them yet. But I guess I want to try and make it as, I don't know, easily that it will work on all test cases simply. So, yeah, I might add another layer of complexity to it. But yeah, good idea. Yeah. 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 It could. Yeah. Could do. Yeah. I'm not sure. I guess I didn't think of that, but um, yeah. I mean, it's. I don't know if it would make a massive difference. Maybe it would. But I'll try and find out. Uh, yeah. Sorry. Yeah. Yeah. Mhm. Yeah. Sorry, repeat what you're saying. Yeah, yeah, yeah. No, 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 sorry, yeah, exactly. Yeah, they're local. So why I did that is because yeah, yeah, because I don't want, I guess I wanted to work on all cases, and I don't, I want to be able to change the refinement ratio, and I guess so. Yeah. No, no, just okay. Yeah, I'll add it to the list. All right, thank you.
So hello everyone, I'm Claudio Miccoli and I work as a simulation engineer at Optimad, which is a company here in Italy, in Turin. And today I will present this work that was carried out in collaboration with another company, Estego, North America, with my colleague Bryden Collins. So today, I will speak about our robust shape optimization of the food and drug administration blood pump. So this work is about a centrifugal blood pump and specifically ventricular assist device that can be used for in order to help people, a million of people that suffer cardiovascular disease. And this is the reason why FDA in America has been promoted the usage of CFD in order to design such a medical device. So for this purpose, we need to, let's say, we have two main requirements. So we want to increase efficiency in order to limit the energy consumption. And at the same time, we want to reduce the risk of hemolysis or blood damage, which is the failure of the membrane of the red blood cells due to shear stresses. So we are responding to the demands of FDA by showing an optimization methodology in order to accelerate the design of this blood pump. So let's start from the CFD model assessed in OpenFOAM. We used this FDA blood pump, which is a benchmark test case, but actually our methodology can be extended to more complex geometries. So we used SnappyX Mesh for the computational grid, SimpleFOAM in order to perform steady computation, steady runs. We treated the flow as incompressible and turbulent. And from our tests, we saw that the standard K epsilon model was the most suitable, let's say, because, you know, for an optimization study, we needed a model that was reliable and robust with no convergence issues, let's say. And finally, we assume the fluid to be Newtonian. And again, this is a large accepted hypothesis from the CFD community for this application, because we assume that the flow will experience, let's say, a level of shear strain rate such that the viscosity can be considered as a constant. For the rotation, we adopted the moving reference frame approach, and we simulated porcine blood in condition number 1, characterized by these quantities and this Reynolds number based on the impeller diameter. This is the computational grid. We have almost 9 million of cells, and we got convergence in 64 hours per CPU. For the validation, we took as a reference the particle image velocimetry results published by FDA, and also the results of Good and Manning, who adopted a transient approach with a sliding mesh technique for the rotation of the impeller. And here you can see the pressure red as a function of the iterations, and our result in red is very close to the result of Good and Manning. That should be more accurate. And it also falls within the uncertainty region, the gray area of PIV. Moreover, we got a good level of convergence in 1,500 iterations. And this is important for an optimization study because you need to do many loops. These are the velocity profiles along 3 different characteristic positions in the impeller region. And at the bottom, you can see a comparison between the particle image velocimetry velocity magnitude field and our CFD results. So if we look at the first quadrant, you can see that our results in red again falls within the uncertainty area of PIV, except for this region where there is an under prediction at the tip of the blade. But on the other side, if you look at the sliding mesh approach, there is a bit of over prediction. While if you look at the diffuser region, you can see that the MRF approach generated, let's say, a result that was closer to the experimental one. Unfortunately, in this case, the uncertainty level for experiments wasn't available. But for example, let's say for the diffuser region, this is a well-known problematic region due to the flow separation. So once we assessed the CFD model and validated it, we moved to hemolysis modeling. So we chose an Eulerian approach in order to solve in a scalar transfer form this transport equation in the passive scalar DI, which is the damage index. This is a convection equation with a source term, and let's say this source term derives from a well-known power law that you can find in the literature, and that's let's say describes hemolysis phenomenon. And this source term depends on sigma, which is the stress field. So again, a large accepted hypothesis is to, or better, a best practice is to use the von Mises relation in analogy with solid mechanics in order to describe the stress states in the fluid, because in this way we hope that we better correlate with the failure of the red blood cells membrane. So we coded a new function object in OpenFOAM in order to compute this stress field by starting from the components of the strain rate tensor. This is the solution algorithm. So we started from the solution of simple form, and we solved the equation number 1 until a steady state, and we computed a mass flow average at the outlet of the passive scalar DI, the damage index. In this bar chart, you can see that there is a relative damage index of hemolysis with respect to 2 pump conditions. This is because actually it's very tricky to predict absolute and reliable values for hemolysis. So the best practice in this application is to normalize all the results with respect to condition number 5. And so if we look at condition number 1, again, you can see that our results falls within the uncertainty bar of experiments, but you can still see a large variety. Actually, if you read all the literature, you can see that a large variety is actually still present depending on the method that you use. But the conclusion is that it's still possible to perform a comparative analysis and thus an optimization study if a trend is present with respect to experiments, and it's the case. So we can move on. First recap. So let's say we adopted this steady MRF approach in order to get a compromise between accuracy and the computational time. But actually, I didn't show it, but we also tested transient simulation with a sliding mesh technique. And as you can see, it is too expensive for an optimization analysis. And concerning hemolysis, we chose the Eulerian approach because it's very fast and we got results in line with the state of the art. So let's move to the optimization part, starting from the design of experiments analysis and the selection of the parameters. We took as a constant the housing geometry, and we chose 4 parameters. So the blade stem distance, P1, the blade height, P2, the stem diameter, P3, and the top fillet radius, P4. And we chose these parameters because they can affect both efficiency and hemolysis. And we used Mod Frontier, which is a commercial package developed at Esteco, in order to carry out the optimization analysis. So for the DOE phase, we performed 45 designs with different methods, interpolation methods, and let's say what was important was uniformity in filling the design space, and uniformity is important if you want to use the initial results of the DOE in order to train a response surface, because we used the response surface methodology, RSM. So starting from the DOE results, we used a Gaussian process regression model in order to approximate 2 surrogate models, one for efficiency and one for hemolysis. And starting from the trained response surfaces, we performed 1,000 points run with an algorithm which is a multi-strategy, multi-objective, and hybrid method, proprietary of Esteco. It's called Pile OPT, in order to retrieve the Pareto frontier. So from this plot, the designer can choose the best configuration depending on his constraints and his targets. Later, we validated 5 points evenly distributed along the Pareto frontier with respect to full-scale CFD simulations. And you can see that the error was lower than 10%. So this means that validation is okay. And the Pareto points, these Pareto points can be considered Pareto frontier designs. Finally, we conducted a robustness analysis in order to study the response of the Pareto points to a variation of one boundary condition. We chose the inlet flow rate, and we started with a mean value here, and we applied a deviation of this deviation here in the table. And in these plots, you can see that this analysis was carried out for 4 configurations, and you can see the deviation in terms of both efficiency and hemolysis. And we can observe that a larger robustness is obtained for high levels of both efficiency and both hemolysis. So here, and this is again an important information for a designer, because he can choose the best configuration depending on what he has. So second conclusion, let's say, starting from a CFD model, I showed you this methodology that offers the possibility to perform, first of all, a DOE analysis to select the parameters, evaluate their range, and to have an initial data set that can be used later to train RSMs. So later we can perform this multi-objective and time-saving analysis in order to accelerate the process of the blood pump. And we also have the possibility to perform a robustness analysis in order to study the response of the model to slight variations of some boundary conditions. As a future perspective, we are planning to repeat the analysis by including Rombox. Rombox is a reduced order modeling and machine learning toolbox developed at Optimad. So we are, it's already possible to couple mod frontier and Rombox, so we can increase the accuracy of this analysis by using reduced order model. And there is also the possibility for a multi-fidelity approach. So you can choose the degree of fidelity depending on, what you want. So these are some references, and that's it. Thank you. The grid, okay. Okay, so yeah, basically we have this exohedral mesh. These are the minimum and target sites. We used 3 prism layers in order to capture the boundary layer phenomena. And let's say we generated this grid because it's very similar to the computational grid of the work that you can find in the work of Booth and Manning. So the guys who performed the transient analysis with the sliding mesh approach. So in such a way, we could make a better comparison, let's say, with the same grid, at least the same number. And also we include a refinement at the interface of the MRF. And for the MRF, in order to decide the dimension of the MRF region, we analyze 3 different regions, and finally we decided to the one that offered the best results with respect to experimental data and the work of Booth and Manning. That's it. Yeah, we're using, for turbulence, the K epsilon standard model. Let's say the Y plus was 50 more or less. But we also tested the K omega SST model. Actually, as you know, it suffers convergence problems. And if you want to perform an optimization analysis, you cannot rely on a model that require the let's say that the user debug and so on. So yeah, the objective was automation in this case. The turbulence contribution, you mean? Yeah. They are included. Yeah, definitely. Yeah. So this part here, actually, so maybe I have a backup slide about that. Okay, so actually we tested 6 methods for the training of responsive phases, all these ones. And finally, we decided to use the Gaussian process, which is actually maybe the most simple interpolation method, just because it provided the best correlation coefficients. And later we used this PyLOPT algorithm so for the virtual validation here. Actually, this is a hybrid method because hybrid between gradient-based and global search methods. And let's say it takes the advantages of the two. I cannot say you more because it's kind of black box because commercial package. What? Sorry. Yeah. Okay, thank you.
Final talk. The final talk for this session will be given by Anna Kovárnová from the University of Chemistry and Technology in Prague. And she's going to talk about model order reduction for Eulerian-Lagrangian direct numerical simulations of particle-laden flows.
Thank you for the introduction. I would like to show you our work on model order reduction for Eulerian-Lagrangian direct numerical simulation of particle-laden flows. First, about the motivation. My colleagues in our lab are developing an OpenFOAM solver for particle-laden flows that is an immersed boundary solver, and it is fully resolved. The flow is treated in an Eulerian framework, normally by Navier-Stokes equations, and the particles are treated separately by DEM. It works pretty well at this point, but there is a problem that for more complicated cases, it can be very computationally demanding. For example, this case at the right side took about 2 weeks to simulate, so that is quite an issue. However, we can use some methods of model order reduction and simplify this system in a way that would also preserve some of its most important properties. Model order reduction for such cases is pretty complicated, so let me first show you how it would be done on a much on much simpler cases, such as this laminar von Karman vortex street with a Reynolds number of 100. When we would do the model order reduction, we would start with our physical problem in the physical domain that we would describe by some PDEs, spatially discretize it, and get a large system of ordinary differential equations. That would be our full order model, and this is the thing that we would be that we would treat in a way that we would be trying to reduce this the dimensionality of dimension of this system. Normally, this is done by the proper orthogonal decomposition and Galerkin projection, which is an a posteriori approach. That means that you need to know the solution to construct the reduced order model. We would have our PDE, spatially discretize it, and then numerically integrate this large system and get our solution in the form of a matrix of snapshots, where each column of this matrix corresponds to the solution saved at one time. We assume that the exact solution of our PDE can be expressed as a time-varying superposition of some stationary spatial modes or spatial structures, and we need to decompose it to this this can be done by proper orthogonal decomposition or POD, which is practically the same thing as singular value decomposition. From POD, we get this matrix of the spatial modes psi, where each column of this matrix corresponds to one spatial structure, and this matrix of their time-dependent amplitudes of the coefficients of the linear combinations, where each row of this matrix corresponds to one time-dependent amplitude. The columns of this matrix psi are orthonormal vectors. That means that their norm is equal to 1, and the rows of this matrix eta are orthogonal vectors, and they are scaled by their corresponding singular values from the singular value decomposition. And they are sorted by their relative importance. That is, the most important one is the first, etc. So that means that if the singular value decay is fast enough, we can relatively easily truncate these matrices and get a low-rank approximation of our data. We then can use this matrix psi as a projector and project this full order model onto a lower dimensional subspace where our new variable of interest are these etas, and this reduced order model is much smaller and much less computationally expensive. This works pretty well for the von Karman vortex street case, as the singular value decay, as I have said before, of the matrix of snapshots is extremely fast. That means that only the first few modes are really important, and we can reduce the dimension to, for example, the number of 4, where, as you can see, it's qualitatively quite the same thing, and but we have a problem that we cannot use the projection for our model with the particles, because the particles cannot be described by the large system of ordinary differential equations, because they are treated in a different framework and they are treated separately. So we cannot use the projection. But even if we go to that, then there is another issue, and that is that our particle-laden flows are usually very strongly transport dominated. the von Karman vortex tree that I have shown you before is pretty much ideal for the classic POD Galerkin approach because it's periodic. It has characteristics of stationary waves, and stationary waves are very convenient for us because one stationary wave is just one stationary spatial structure, while our transport-dominated cases, such as this traveling disk, are usually have characteristics of traveling waves, and traveling waves are extremely inconvenient because the solution at one time cannot be expressed as a linear combination of solutions at some other times. Concerning this, when we take this traveling disk and save it into a matrix of snapshots, then the singular value decay for this matrix is extremely slow, and we would need a large number of modes, that is a large number of spatial structures for a sufficient approximation. So it would really make no sense to do that. So how to solve this issue? The problems with transport are that is the traveling disk cannot be expressed as the linear combination when we look at it from a stationary frame of reference. However, we could choose another frame of reference. We could choose a frame of reference that would be traveling along with the disk, and from the point of view of an observer in that frame of reference, the disk would appear to be stationary. It would be just one stationary spatial structure, and that means one non-zero singular value. Now, that would give us a low-rank approximation of our data that would be discrete in time, but we need it somehow continuous in time. So normally we would do that by the projection, but there is a problem that there is another problem with the projection, that we might have a system that has multiple different transports. We are using a method called shifted proper orthogonal decomposition, or SPOD. It was developed by Professor Rice from Berlin, and this method is able to sort the data into their optimal frames of reference, and it works pretty nicely. However, it doesn't give us any projector that we could use to project the full order model onto the lower dimensional subspace. Instead, it gives us multiple of them, that is one for each frame. So we cannot use the projection, so we are using interpolation instead, and in particular we are using interpolation by artificial neural networks. The resulting method is called the shifted proper orthogonal decomposition with interpolation via artificial neural networks, or SPODIAN. It is, unlike the projection-based methods, it is mostly data-driven. We just need our matrix of snapshots and some information on the transport. Then we perform shifted POD on this matrix, get our matrices of the spatial modes psi and of the time-dependent amplitudes eta. We then use these etas as training data for our neural network, and the neural network gives us an interpolates between them and gives us a time continuous approximation. This is done in the model preparation phase. In the model evaluation phase, we just multiply these matrices psi with the spatial modes by our time continuous approximation of the amplitudes, then shift it back and add all the frames together to get an approximation of our original variable. Now, some examples that were simulated by our in-house solver that I have shown you in the motivation slide. I forgot to mention that this solver prescribes describes the presence of the particle by a lambda field, where a lambda field is equal to 1 inside the particle and 0 outside, between 1 and 0 on the boundary. So this particular case is a case with 3 disks in a rectangular domain, where one of the disks is stationary and the other 2 are moving with prescribed velocities. And when we see some results of model order reduction, then we can see that for simple POD, the singular value decay is extremely slow, and also the approximation is not very quality. Even if we use the first 20 modes, there are still these major oscillations present because POD wasn't able to capture the transport. However, when we use shifted POD is able to sort the data into their own frames of reference. It needs just 1 mode for each frame, and that is 3 modes in total. A pretty similar thing, maybe less severe for the velocity field generated by those disks. Another case was a case with 2 falling disks, where the disk velocities were not prescribed, but rather they stemmed from some coupled fluid-solid interactions. And here, our solver gave us information on the positions of the disks. That is, we only had discrete information. That is, we only had discrete transport operators for shifted POD. We solved it by using another neural network to also interpolate between the positions to get time continuous shifts as well. And again, pretty similar thing for the velocity field generated by the movement. So to conclude, we are developing a method of model order reduction for particle-laden flows. We are using shifted POD for a low-rank approximation of our data, and then artificial neural networks to get a time-continuous approximation, the reduced order model. We are able to treat cases also with discrete transport operators, but by using another neural network to interpolate also between shifts. And as the next step, we would like to extend this method to also work for parameterized systems, which would be really useful because we could also interpolate between the parameters. Here at the bottom of this slide, you can see how we are doing it for normal POD without shifts. We have prepared some cases again for the von Karman vortex street, where we prepared cases with Reynolds numbers 50, 60, 70, 80, etc., and done the model order reduction, and we prepared and we were able to interpolate between those Reynolds numbers and get, for example, this this case with Reynolds number 81, but there is still a long way to go. So thank you for your attention. Yeah, we haven't tried it yet for such big systems, but we have tried it for a system with 20 particles, where we know that shifted POD works and converges and is better than normal POD. But I assume that for such big systems, there is still like a long way to go. That both POD and shifted POD wouldn't be performing very well. No, but I assume it would be quite slow, but not as slow as these few particles. Yeah, it would be like something in between, I think. But